Hey guys, welcome. This video was not intended to be at all. For some reason, I couldn't fall asleep the whole night, and so math for breakfast. The next video I was going to make was going to be a multivariable calculus video on line integrals, but since I noticed that you guys have recently been really benefiting from the review videos I posted, I thought maybe one last one final review. All right, so here it goes. And so what I'll say to you is first, thank me later, you're welcome. And second, just when I thought I was out, they pulled me back in. Now, to make this video very meaningful, I had to go back further and further to the older FRQs. So I pulled these three questions from the 2011 and 2012 FRQs. Now, this one is from the 2012, and then it's problem 3. Now, let's get at it, because I want to do this and maybe try to power nap because I have a really long day. All right, now the function f is given here, and g is defined as the integral of f from 1 to x, right? And so in part A, what we have to do is first find g of 2 and then g of negative 2. Let's start with g of 2 as they've written, and so g of 2, by using the definition of g, is going to be the integral from 1 to 2 of f of t dt, right? Forgive any stuttering, anything that happens. You're welcome, like I said. All right, now, so this we can interpret as the area bounded by the graph of f and the x-axis between x equals 1 and x equals 2, right? And so then that'd mean the area of this little right triangle right here, right? This little right triangle right there. Okay, this little right triangle right there, right? Okay, now, since I've highlighted the triangle, I can undo that part. And so that's one leg being length 1, and then this is 1/2. You can more carefully figure out that this is in fact 1/2 by finding the equation of this line, then plugging in x equals 2 into it, but don't do that. That's too much. You should be able to figure out that it's 1/2. So this is 1/2 base times height. So this is from the 1/2 BH and the area of a triangle, and then the base we can use one of the legs, so that's 1, and then the other leg is 1/2. But remember, this is below the x-axis, and area below the x-axis is negative, so we throw in a negative sign right there, so the answer is -1/4. That's g of 2, right? Okay, and then for g of -2, right? G of -2, what we're going to do is, well, use this definition again, and this time we'd have to write the integral from 1 to -2 of f of t dt. But wait, to make sense of this as area bounded by the graph of f and the x-axis, we need this smaller number to be the lower limit. But then we know that integrals have that property where if we throw a minus sign in front of the integral, we can swap the limits of integration, so we'll have to do that first. So then we do this, right? And then now what we'll have is that this is the same as negative of whatever the area is between -2 and 1, bounded by the graph of f and the x-axis. So -2 is right here, right? So from here to 1 all the way up there, just to distinguish, I'll shade in a different color. So it's this blue triangle plus this semicircle, right? Now, the blue triangle is pretty obvious. It's got area 1/2, and then base is 1, and then the height is 3, so that's -3/2, right? Well, sorry. This minus sign is from that. But yeah, it will be -3/2. And then we also have the semicircle, and so I need to make space. I suppose I could just write that as -3/2 right there, and that would be all the space I need. So, well, +3/2, but again, that minus sign will make it -3/2. But then this here, the semicircle, right, it's area below the x-axis. And so then it's going to be pi r squared over 2, but it's going to be negative as it is below the x-axis, so it's going to be negative pi times r is 1, so 1 squared over 2, right? Okay, so if we work this all out, then we have -3/2 plus positive pi over 2. So if we lead with the positive, that's going to say pi minus 3 all over 2. Yeah? Okay, cool. All right, so then part B. Part B says, let's do this. Part B says, find g prime of -3 and g double prime of -3, or otherwise say that they don't exist. Now, since g is defined as the integral of f, we see that g prime, right, g prime of x more generally is going to be the derivative d dx of the integral from 1 to x. Oh wait, have we heard of the derivative of the integral? Yes, that's our main guy or gal, the fundamental theorem of calculus, which tells us that this is simply equal to f of x, right? So then g prime of -3 we see is just going to be f of -3, and f of -3 is what? Well, we go to -3, right? And we project onto f to figure out the y value, right? And we can clearly see that that's 2. Yes, you could be very meticulous and figure out the equation of this line and plug in -3 into it, but don't do all that. This is not dubious. It's clear that it's positive 2, right? So we're going to go with that. So positive 2, right? Okay, cool. And so then g double prime of x then will have to be f prime of x, because, well, g prime is f, so then g double prime should be f prime. Okay, cool. So this time, since we want g double prime of -3, what we have to do is figure out what f prime of -3 is. Okay? But then that's the slope of f at -3. Well, we have a line there, and if you count the slope carefully, what you'll find is that it's got a rise of 2, because, well, that's the difference between this y value and that y value, and that's 2, and a run of 2 also, and that's this horizontal distance from -4 to -2. So we have 2 over 2, and that we know better as 1. So 2 over 2, which equals 1, right? Okay, cool. So both of them exist, and we just found them. All right, cool. Next part. All right, so here we have to figure out where we have horizontal tangents and classify them as relative max and min. Now, horizontal tangents, right, that would be for g, and so that means g prime is equal to 0, right? But wait, we just got done saying that g prime of x is equal to f of x. So figuring out where g prime is equal to 0 means figuring out where f of x is equal to 0. Fine, where's f of x equal to 0? Right there, right? And then right there, right? Okay, cool. So we've got two values where f of x is equal to 0, therefore where g prime is equal to 0. So let's draw a number line for g prime. And so that's for f, right? But let's label it g prime because our main item is g, right? Okay, and so those two are x equals -1, x equals -1, and then the other one is x equals +1, right? X equals +1, and then we do the number line analysis, the usual, right? So we want to know, is g prime positive or negative to the left of -1? Well, we can see immediately to the left of -1, the value of f is above the x-axis. That's the value of g prime is positive, is what we're saying in saying that. So we've got positive, and then immediately to the right of -1, well, clearly f is below the x-axis, so g prime is negative, and then, well, to the right of +1, f is below the x-axis, so g prime is negative. So we see that we've got neither local max or min at x equals 1, but we have positive to negative for g means the slope of g going positive to negative means we have a local max at x equals -1, right? Okay, cool. So that's that for part C. This is moving more efficiently than I expected, which is good, which is good, which is good. Okay, so next is we look between -4 and 3, and we have to do what? Find all values of x for which the graph of g has points of inflection and give your reasoning. Okay, cool. So points of inflection. First, we need to come up with the candidates for points of inflection. So candidates for points of inflection are where g double prime is equal to 0, or, don't forget, or undefined, right? Or undefined. Okay, so let's see. Now, we said that since g prime is equal to f, we've already said this, I'm making it like pretty obvious for anyone who isn't paying attention, g double prime of x is equal to f prime, right? So we're trying to figure out where f prime, the slope of f, is equal to 0 or undefined. Now, there's only one place where f prime is equal to 0, and that's right there, where we have a horizontal tangent to the graph of f, right? So that's x equals 0, so one candidate is x equals 0, but there are a bunch of places where f prime and therefore g double prime is undefined at any sharp turning point. That's x equals -2 right there. There's a sharp turning point or a cusp. So x equals -2. That's why it's so important that you don't forget this part, right? And then where else? This 2 counts as a sharp turning point. It's not smooth right there. So x equals -1, right? And then where else? Clearly x equals 1. So these are all the candidates for points of inflection. But candidates I say because, well, we need to make sure that we change sign. That is, g double prime goes from positive or to negative or the other way around about these places in order for us to claim them as points of inflection. So this number line this time is for g double prime of x, and we throw on these guys. And I'm going to do it in black just to keep it interesting, just to keep life interesting. So -2 here, and then -1, right? And then 0. I mean, I am making it interesting already by staying up all night, like being insane and making a math video first thing in the morning. Okay, so immediately to the left of -2, we're analyzing the slope of f because that's what g double prime is, right? It's f prime. Okay, so immediately to the left of -2, we see that f prime is positive. So g double prime is positive, and then to the right of -2, it's negative. Ah, cool. So this is a point of inflection. X equals -2. And this number line would suffice as like the analysis and the explain your reasoning part. And then at -1, we see that we have the slope of f is, and therefore g double prime is negative, but it continues to be negative. So negative to negative on either side of -1. See, on this part, it's still negatively sloped, right? Okay, f is, and therefore g double prime is negative. Okay. So then at 0, it's clear that you go from negative to positive for f prime, and therefore for g double prime, so negative to positive about 0. And then finally at 1, well, we go from positive to negative. So the points of inflection are -2, 0, and 1. Yeah? Okay, cool. I'm not going to write more. That should be sufficient. On to the next one then, huh? Okay, all right. So what's the next one? Let's see. So it is cover this, cover some more, and yeah, it's this one. This is pretty cool. And I want another copy of it right there, the visual anyway. Okay, cool. So read it. I have k is greater than 0. Important. Right, but do not evaluate an expression involving an integral that gives the perimeter of R. So they start with the perimeter, which is kind of strange. And in review part 3 for the 2020, so my review video part 3, the third one, I said that I had never seen any question that involved a line integral on the BCFRQs except that one question that was there. Well, okay, apparently there was another one here, and this one was from the 2011. And so here we have to do a line integral here because they're asking us for the perimeter of they're asking us for the perimeter of this fella. So hold on. Yeah, I need to kind of erase this part. It's not like perfectly on top of my line. Okay, whatever. Like we'll live, right? All right. Okay, so first for the perimeter we need to draw, and this is why I wanted 2 copies of the visual. We need to figure out how long that is. That's clearly just k long, right? It's k units long. And then we need to figure out how tall this is, right? Because we need to go around the shape, right? Okay, and that's clearly the y value at k, and that's e to the 2k. So far we have k plus e to the 2k. And then in this part, right? In this part we have just 1, right? The y value there. And finally, and perhaps most importantly, we need to figure out this part, and that's where we need an integral, a line integral to be specific. So we have 1k, and then e to the 2k, and then, so for part A so far, we have 1 plus k plus e to the 2k, and then we need to do a line integral. And remember, the line integral, if your function is in the form y equals f of x, would have to be the integral from whatever limits of integration. So here they'd have to be 0 to k, right? Because that curve right there concerns those x values. And then it's going to have to be the square root of, right? Sorry, one more. The square root of, that's better. or I feel better anyway. The square root of what? The square root of 1 plus dy dx squared, right? So it's going to be the square root of 1 plus dy dx squared. So the square root of 1 plus, and then since the function is this, dy dx is f prime, right? And so that's going to be 2e to the 2x, so that's not so hard. So 2e to the 2x, poor writing, 2e to the 2x squared, and then of course dx outside of the square root. Okay, so you put these guys together, and that answers part A. So let me shrink this and throw it right there. So that's a complete answer for part A, and yeah, nothing else to say about that. Part B. Part B says the region R is rotated about the x-axis to form a solid. Find the volume V of the solid in terms of K. Okay, this is pretty straightforward. Since there is no gap between the axis of rotation and our region, we know that we're going to use the disk method. And so that's pi and then integral from 0 to K and then R squared dx, right? Well, clearly R here is the function f of x, so it's just going to be f of x squared, and then dx. Now, given all my spiel about not having slept, blah, 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 I will let you do this. Actually, I'll finish it with you. Why not? Why not? Why not? Because we need it for the next part. I wasn't going to finish it, but so this is V, right? The volume. Okay. And V, it's technically V of K, right? As you'll see, but because it will be in terms of K, but it's fine. It's fine. So we'll just write simply V. Okay, so that's going to be pi and then integral 0 to K, and then f of x squared is e to the 2x squared, right? Back-to-back exponents say that that's e to the 4x, right? And then otherwise dx, right? Okay, now the integral of this is pretty straightforward. You should find that it is pi over 4 and then e to the 4x, right? Okay, cool. And so we need to evaluate this from 0 to k. So we see that v, and perhaps we should get rid of this since we don't need it, and we need the space for part C, right? So so we see that v is going to be, it's going to equal plug in k, and then that's going to be pi over 4, and then e to the 4k, 4k, and then minus plug in 0, so that's e to the 0, which is 1 times pi over 4, so minus pi over 4. Yes, you can factor a pi over 4, but don't do it. As you'll see, it'll be nicer to keep it this way for part C. So part C is the volume V found in part B changes as K changes, and if the rate of change with respect to T of the variable K is a third, determine dVd. So this is a related rates question when K is equal to 1/2, right? So all we have to do is take the derivative implicitly of this with respect to T. So on the left, we're going to write dV dt equals, on the right, we're going to have, well, the derivative of this is going to say 4 times pi over 4, and then e to the 4k, and then don't forget by chain rule dk dt, right? dk dt, and then the derivative of this is 0, and that's why I wanted to keep this the way it is, uncomplicated. Yeah, okay. Now this here is, we're told a third, right? So we can replace that with a third, and then otherwise they told us when k is equal to 1/2, so this is going to say 4 times 1/2, that's going to say 2 then, and so I'm going to change that to a 2, right? And so then let's see, this here and this here cancel, so all simplified is going to say pi over 3 e squared. Yeah, okay, cool. Alright, one more, and maybe I could just like fall asleep and ignore the rest of my day. I wish. Like, that's called wishful thinking. Like, okay, and finally, problem 6, and this is from the 2011 BCFRQ, and this came with a picture, but the picture only concerned part D, where we had to do error bound, and remember, error bound is not on this year's AP, so we don't have to worry about part D, and so we don't have to worry about the picture that was given. For answering parts A through C, which we're going to do to finish, we just need this definition of F. Okay, cool. A, it says write the first four non-zero terms of the Taylor series for sine of x about x equals 0. So it's saying the Maclaurin series for sine x, and write, using it, the Maclaurin series for sine of x squared. Okay, now, e to the x Maclaurin series, you should have memorized sine of x. Well, if you're really, really cool, then you should have it memorized, like some of us, if you're really cool. And if you're not cool, well, I suppose you could use the definition of the Taylor series to come up with it. But you should know that it's n equals 0 to infinity, and then it's negative 1 to the n, and then it's x to the 2n plus 1 divided by 2n plus 1 factorial. So I just happen to memorize these things because, like, well, I don't have a life now. Just kidding, because I'm cool, like that. Okay. All right. So then if you have this, it's easy to get to the Maclaurin series for sine of x squared. You just replace this x with x squared, meaning you replace this x with x squared. So then we see that sine of x squared, and I keep calling it Maclaurin series because that's what a Taylor series centered at 0 is. It's a Maclaurin series. So sine of x squared is n equals 0 to infinity, and then it's negative 1 to the n, and then, as I said, we need to replace the x with x squared, so x squared to the 2n plus 1, otherwise nothing else is going to change, right, divided by, and then 2n plus 1 factorial, right? Okay, cool. Now, so we see that we can go from well-known Maclaurin series to modified version of them just in this little kind of manner or modification. Okay, all right. N equals 0 to infinity, and I'm saying we can simplify this a little bit. So this, and then what is this? Back-to-back exponents say that we multiply these, right? So that's going to be x to the 2 times 2n plus 1. That's going to be 4n plus 2, right? And then all this divided by 2n plus 1 factorial, right? 2n plus 1 factorial. Cool. All right. So this answer is part A. And part B says, write the first four non-zero terms of the Taylor series for cosine. Why do they keep saying that? They could just say Maclaurin series for cosine and use the series for sine x squared found in part A to write the first four non-zero terms of the Taylor series, so the Maclaurin series for f. So basically we can clearly see that f is defined as this plus the cosine Maclaurin series. So we just need to write the cosine Maclaurin series and combine the two. And it says write the first four non-zero terms. I see that in A, I haven't fully answered the question in that I didn't write the first four non-zero terms. We kind of need to do that, so I guess I could write it here. That just amounts to plugging in different n values, right, starting with n equals 0. So first, for sine x, simply sine x, we could do this almost off memory. If you plug in n equals 0, you're going to get an x, right? So it's x, and then it's minus x cubed. You could do it more carefully. I'm just going to do it off memory. Over 3 factorial, it alternates, so it's going to be plus x to the 5th over, you can see that it alternates because of that anyway, over 5 factorial, and then it's going to be minus x to the 7th over, and then 7 factorial, right? And so then, as we said, for sine x squared, you just need to change these x's to x squared. So I suppose the easiest way to do that, to come up with the sine x squared first four non-zero terms, is to even ignore this, right? Ignore plugging in n equals 0, blah, blah, blah into this, and just change these x's into x squared and simplify, right? So where appropriate. So that's going to be x squared. No simplifying required there. And then in this part, it's going to be x squared to the 3rd. So that's going to be minus x to the 6th over 3 factorial. And then next is going to be plus, and this part is going to be what? X squared to the 5th. So that's going to be x to the 10th over 5 factorial. And then minus x to the 14th over 7 factorial, right? Okay, cool. All right. Now, just to check, sanity check, right? If we plug in n equals 0, we're going to get x squared. This is negative 1 to the 0 over, and then it's going to be, what is it going to be? 2 times 0, so that's 1 factor. So we're just going to get x squared. So yeah, it does work, right? Okay. We didn't even need the general terms really, right? Because they didn't ask for that, but it's fine. So I need this space, so perhaps we get rid of this, or like not all of it. Maybe we need it. I didn't read the question in full. So maybe we need it. I don't know. Let's keep this part. Okay. So what is this going to say? This is going to say, let's put this right here. That's all the space I have. Okay. Well, we were on the cosine part, right? Yeah. So part B, right? Part B, cosine. So you see, like, other than, like, you know, plugging in x squared for x here to figure out sine of x squared, what we could do is we could differentiate and integrate Maclaurin series. I have lots of videos on these, so check them out if you need the extra practice. But what I'm saying is we could get to the cosine Maclaurin series very easily by differentiating the sine Maclaurin series. So you really only have to memorize one of them. Well, we know cosine is the derivative of sine. So if you take the derivative of this, what you're going to get is sigma, right? N equals 0 to infinity. Now, the negative 1 to the n is not going to be affected by differentiating because, well, if you write like minus 2x plus x cubed, blah, 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 when you take the derivatives, the signs are going to stay right where they're at. So the negative 1 to the n is not going to be affected by differentiating. But we drop this power, right? So that's going to be 2n plus 1, and then decrease it by 1, so that's x to the 2n, and then we divide all this by 2n plus 1 factorial, right? Because that's what's in the denominator already. All right. Okay. And again, these are constants, and the constants that were there are not affected by differentiating. Now recall that 2n plus 1 factorial, right? That's going to equal 2n plus 1 times 2n factorial. So if you use this, you see that here you can replace that by 2n plus 1 times 2n factorial, wherein you could get rid of this, and so the denominator just turns into 2n factorial. I'm saying you can simplify what we have inside of sigma for the cosine Maclaurin series over here a little bit and write that cosine x, right, Maclaurin series is equal to n equals 0 to infinity negative 1 to the n, and then x to the 2n over 2n factorial. Okay, so it says, write the first 4 non-zero terms of this. So if we plug in n equals 0, we're going to get what? Well, negative 1 to the 0, and then x to the 0, so that's 1, and then 0 factorial, so we get 1. And then when n is 1, we're going to get negative x squared over 2 factorial, right? When n is 2, we're going to get positive x to the 4th over 2 times 2, that's 4 factorial. Got it. And then we need 4 non-zero terms, and then it's going to be what? Minus when n is 3, and then x to the 6th over, and then it's going to be what? 2 times 3, so 6 factorial. Got it. And so for f of x, right, for f of x, I'm going to write f of x in black, which we are told is the sum of sine x squared, so this fella, and cosine. So this, well, we just have to add them up. So we need the first 4 non-zero terms for f, right? And the sum of them, right? The sum of these two, this one and this one, right? Well, see, the constant term leads, so that's going to be 1. And then the x squareds, they both appear. And notice that this x squared is like really 2 over 2x squared, because it's 1x squared, right? And so 2 over 2x squared minus 1 over 2x squared is going to give positive 1 over 2x squared. So simplify in this manner. And so if you did, or combine in this manner, well, what's next? Actually, I'll write it. I won't skip details. I was going to skip some details. I was hoping I can cut some corners. So there's no x to the 4th there. So we could just put this in. So I realized that that part is pretty easy. X to the 4th over, and then it's going to be 4 factorial. And then this here, though, and this here can combine. So the common denominator will mean that you multiply this top and bottom by 6 times 5 times 4. That way the denominator becomes 6 factorial like it is here. And if you do all that, what you'd have to write correctly is negative 121 over 6 factorial and then x to the 6th. Yeah? Okay, cool. And so we can very efficiently answer the next part, part C. It says find the 6th derivative of f when evaluated at 0. Well, the 6th derivative of f when evaluated at 0 has got to be the coefficient of x to the 6th in the Maclaurin series for f. And so that's got to be negative 121. This is going to be the sixth derivative of f at 0. Well, the 6 factorial comes from, like, the denominators having to have factorials. But the rest of the coefficient of x to the 6th, that's got to be, because remember, the definition of the Taylor series is like fn, the nth derivative of doing Maclaurin series over n factorial, and then it's x to the n, right? And so then this is just that. And so this here has got to be, when n is 6, that. Yeah, okay, all right. I drew enough over it. I hope you enjoyed this, and yeah, thank me later. I hope you do really well on your test, and good luck. And follow Jesus. He's awesome. Take care. Bye.